Greetings, everybody. It's a very nice pleasure for me to be here, and I would like to thank the organizers for the opportunity and for organizing this great conference. I'm going to summarize different topics related to the possibility of dark matter inside neutron stars or in their surroundings, and I will sort of land in the application of deriving some uniformly rotating compact star with a dark matter halo. Many of the things that I have prepared have already been presented, so I will not spend too much time. I will just probably flash or even skip. So I can tell you something about the physics of compact stars, just for somebody that is not so familiarized. And then I will consider a couple of scenarios, basically axions and other types of photons, bosons. And then I will discuss the possibility of the neutron star collapse into a third family. And finally, I will say something about this application or derivation of the rotational configurations. So the motivations, we have a lot of new ways of studying neutron stars in the framework of the multi-messenger approach, but also from nuclear measurements. We know a lot about the question of state, and yet this is not completely well settled down. However, there's a great progress in the last years. So when considering neutron stars, we can think of the QCD phase diagram. So the neutron stars are located somewhere in the low temperature and high density or high chemical potential axis, and depending on the content, or depending on the position of the neutron stars here will be the content. So there are different possibilities like just neutron stars made of simply protons and neutrons, but there could be neutron stars with hyperonic content or bosonic condensates, and of course the confined quark matter and so on. So when it comes to neutron stars, what is very important is to understand the question of state and the role it plays when it comes to stiffness. And this is basically how much matter will oppose against the crunch or like the compression of gravity. And this will dictate not only how large or smaller compact stars, but also the maximum mass, which is an unknown quantity that is also being under study. And then if we consider dark matter candidates, one of them, as we have heard, are the axions. So, for instance, I would like to just remember this work where, together with some collaborators, we consider the action as derived from an alternative theory of gravity. Basically, a torsional field could create, could play the effect of an axial field, and if that was the case, this could interact with neutrinos by flipping the spin of the neutrino. So this could be hopefully and observable for free streaming axions and interactions with neutrinos. Now, when we consider axions inside the neutron stars, just as Eduardo has just mentioned, one possibility is to study the axion cooling. And back some years back, Armen Sedrakian started to do this type of calculations. Probably there are more refined studies nowadays, but the idea is that the emissivities may change because there are channels that can be available for this kind of cooling, and with this some simulations can be performed and try to be compared with the non-action with the case without the axions. Also, new approaches considering axions trapped in quark matter. For instance, in the recent work, we have been studying the possibility of coupling the axions to some NJL model and to try to study the properties, especially for different scenarios, for just neutron stars or for hot dense matter, like the one that could be produced in the mergers of neutron stars. So this is like one of the work in progress, and one of the ideas that could probably bring some information about the content of axions. There are other groups that have been also considering effects on the stability on the neutron stars. So in this case, in this work, the authors consider that the axions can change the topology of the mass-radius relation, just like a first order phase transition could do for instance, to other type of matter, right? And when it comes to this, if you consider models that do not have phase transitions, that assume that at least in stable neutron stars there will be no phase transition to quark matter or so on, then under this assumption, whatever that could be dark matter, they could also create instabilities. And in some extreme cases, and for certain parameter values, it's possible to find the so-called twin stars configurations, where two stars have the same masses but different radius. And if that's the case, of course, there could be some signatures when there's evolution from one of these configurations to another, and this will be related to a compactification of the star, leading to some energy provided by the mass defect between the configurations. So this could be another smoking gun if detected, of course. Another candidate is the sexaquarks, which is basically a boson because of the spin that is belongs to the standard model. Is not as exotic as axions. However, this could be also produced in neutron stars. Once the chemical potential of the sexaquark appears, it starts to, in the interior of neutron stars, so as the density increases from the surface towards the interior of the neutron star, the baryonic chemical potential starts to increase, and then different baryonic species start to be populated, and the sexaquark could be one of these candidates. We will hear more about this from Mahube that is here later today, so I just wanted to include it for completeness. So coming back to the question of the dark matter in neutron stars, there are these three types of possibilities where the dark matter is inside the neutron star, or when the dark matter is all over the place, not only inside or outside, but also when it's confined in the core, or when it's just uniformly distributed. So about this, we used with Alexei and Violeta, we've been discussing this possibility. We use the same model that was presented by Eduardo, based on this article here. But what we found, this is interesting, is that the chemical potentials of the baryonic component and the chemical potential of the dark matter component follow this kind of relations that end up being like proportional by some constant. And in this way, it has been possible to scale the dark matter into a halo. And with this, we could create an equation of state that will have the baryonic and the halo properties just by choosing some scale parameter. And with that, it has been possible to use a rotational code to try to study these rotational configurations that, as a first approximation, they are just uniformly rotating, which might not be is not the ideal case, but it's like the first approach to study how these halos, how these configurations will change. So what you see here is the static case without halo, then you see the static case with a halo, and then the rotational configuration. And as you might assume from the physics of neutron stars, this more or less corresponds to a 20% or so in the increase of the mass from the rotational configuration. So this is at the Keplerian frequency. It's rotating at the Keplerian frequency, and these are the parameters for the edge of the halo, where we just stop the table of data are given here in case somebody is interested into this. So it's very interesting because these halos may interact, as it was mentioned today in the morning, like studied tidal deformabilities or in the mergers, or perhaps cooling of neutron stars, because the gravitational field, gravitational waves can change the frequency of the photons and so on. And I would like to, beyond the physics of neutron stars, but going back to dark matter, I would like to take the opportunity to introduce you to some experiment, which is basically a collaboration that is searching for dark matter and also to study other type of fundamental physics, and it's called the CREDO Cosmic Ray Extended Distributed Observatory, that is looking for cosmic rays that that are not only located in a particular site, but that they can be distributed all over countries or all over extended territories. And the idea here is to try to establish many detectors all over the Earth to study this kind of showers that are expected to be correlated. And by studying these correlations, the hope is to try to understand what is the primary particle that produces this kind of extended showers. So the collaboration started by invited everybody to use their telephones as cosmic ray detectors by installing an app. But also now the net is all over the world, and it's also connected to more dedicated observatories, and is expected to be improved by more sophisticated detectors than not only the smartphones. So the message is that you can collaborate, you can participate if you want with different approaches like theoretical models for dark matter, or even if you want to look into data or any others, the collaboration is open to everybody. And with this, I would like to conclude. Thank you very much.
Thank you. Questions?
So in these rotating stars, do you consider the dark matter and the baryonic matter to rotate with the same velocity?
Yeah, it's a solid body in this first approximation. The whole dark matter is admixed. It's like in this model, it's all uniform. But of course, the halo contains only dark matter, but it's rotating as a solid body. So that's why what we got is more or less what you were expecting, as if it was just an equation of state of neutron stars. Of course, we want to go beyond that, and we will continue doing perhaps a different approach that will have different rotational frequencies and different other considerations.
Okay, so can you say what kind of configurations do you have in mind you want to study first? Which do you think are most physically relevant?
Probably having different frequencies of the rotation of the halo and the rotation of the neutron star.
Yeah, so highly rotating halo, or
that depends on what kind of dark matter interactions are you considering. So probably the neutron star will rotate faster. Depends on your model, right?
Yeah, so that's my question. What model do you want to study?
Right, we can start with any of them. I mean, we need first to set up the calculation.
Any more questions, David?
Yeah, thanks for the talk. I'm curious how dark matter can impact that maximum rotation velocity above which a neutron star simply like falls apart. Is it Keplerian limit?
Yeah. So because in this case we were just considering the mixed matter, so it just behaves as a solid uniform body. So in this very rough approximation, the dark matter and the baryonic matter will all just be expelled at the same frequency. But ideally they should have different Keplerian frequencies.
Sure. But in this simple scenario, what's your intuition? That Keplerian frequency in the presence of dark matter, is it larger or smaller than in its absence?
But it was here at the. So this is the rotation of the mixed phase. You mean in comparison to the only hadronic matter?
Yeah, right.
Okay. The curve should lie over here, okay. Indeed, because it's just sort of a scale. So the halo just makes it larger.
Okay.
I don't see any more questions, so let's thank the speaker again.
Thank you.